Hello, my name is Akhmetov Alim, CST2409079, and today I would like to present the application of mathematics in economics, volume calculation, and mechanics. It will be the overview of derivatives, volume calculation by using the washer method, and the moments with center of mass. So, let's begin with the application of derivative in economics. In this part of the presentation, I would like to talk about the 3 points: the cost function and average cost function, revenue function and average revenue function, and the profit function and average profit function. So, what is the cost function? A cost function, by definition, represents the total cost associated with producing a certain quantity of goods or services. So the formula is Cx equals fixed cost plus variable cost per unit multiplied by quantity. The derivative is a marginal cost. It's the increase in cost from producing one additional unit. So the MC, marginal cost, equals dC divided by dx.
So, the cost function. Cost function, we'll be writing it's like a Cx. What is a cost function? Cost function is a fixed cost plus variable cost per unit multiplied by x. So, let's have an example. For example, Cx equals 100 is the fixed cost plus 5x. So the variable cost unit is a 5 and x is x. So if we want to find the derivative, the marginal cost, we should take the derivative of Cx. So it will be the just 5. So what this just shows us, that means that the actual cost for the only one unit is 5.
Let's move to another one, average cost function. Average cost function represents the cost per unit of production. The formula will be the AC x equals the Cx divided by x. The derivatives indicates how average costs change with the production quantity, DAC divided by dx.
So next one is the average cost function. So formula is AC, average cost x, equals Cx divided by x. So, for example, let's have the same example. Cx equals 100 plus 5x. So, the AC x will equals the 100 plus 5x divided by x. So, it will be the 5 plus 100 divided by x. So, what's even that? It shows that how much we will spend on a one average product. So as you can see, if we have a more excess, so more quality, more quantity of the product, so will be the cost of one product will be less than if we will have only one product.
A revenue function represents the total revenue from selling a certain quantity of products. So the formula will be the Rx equals price per unit multiplied by quantity sold. The derivatives shows the margin revenue, MR, it's a change in total revenue from selling an additional unit. MR equals dr divided by dx.
So revenue function. Revenue function, we have Rx equals price per unit multiplied by x. So, for example, we have a Rx equals 20x. So that means if we'll take the derivative of it, that means it will actually equals the marginal revenue. What is the marginal revenue? Marginal revenue is shows the total revenue from selling the one additional unit. So if we'll take the derivative of it, we'll just margin revenue will be equals just 20. That means from the selling one object, we will have 20 something, for example, ringgit or dollars.
An average revenue, by the definition, represents the revenue per unit of the product. By formula, it means that the AR, average revenue, equals Rx divided by X. So what's the derivative does? It indicates how average revenue change with the production quantity, DAR divided by DX.
So the average revenue function. So the formula is AR x equals Rx divided by X. So let's have the same example. Rx equals 20x, so the Rx Arx will be 20x divided by x equals just 20. So the derivative will show the changes in average revenue per unit. That's it.
A profit function, by the definition, represents the difference between total revenue and the total cost. So the formula should be the PX, profit, equals RX minus CX. The derivative, the marginal profit, change in profit from producing one additional unit. So the MP, marginal profit, equals DP divided by DX.
So let's move to the last one. Last one will be the profit function. Profit function. So what is the profit function of the formula of it? It's a PX, profit, equals the revenue minus cost. So let's have an example with the two previous one. So the PX equals 20x minus 100 minus 5x. So it equals 15x minus 100. So if we'll take the derivative of px, so we will get we will indicate the profit changes with one more unit is produced. So if you're taking the derivative, so there will be just 15. So the actual profit of our work is 15.
Average profit function, by the definition, shows the profit per unit of goods. So the formula is the AP, average profit, equals PX divided by X. So the derivative indicates how average profit changes with the production quantity. So the DAP divided by DX.
Okay, now the average profit function. Profit function. So what the formula of it? It's AP x equals px divided by x. So have an example from the previous one. From the px equals 15x minus 100. So AP x will equals 15x minus 100 divided by x. So it equals 15 minus 100 divided by x. So and this one we can show the how will the just we will see the profit from the each one of the product. So if you will, as you can see, if you have the more products, then we have get more money. For example, ringgits or dollars.
So, for the application summary, I would like to say that the derivatives provides insights into the maximizing profits, minimizing cost, and understanding production efficiency. So, let's move to the another section, the washer method. So, it is a mathematical technique used to calculate the volume of a solid of revolution. So it is applied when the region being revolved and has a hollow center. So here is the formula of a washer method. We will see the examples of how to use it a little bit after that. So here is the number one, example number one. The volume of revolution between two curves. That's a little question, interesting, and represents how to use the washer method. So we have to find the volume of the solid obtained by the revolving the region between the curves y equals x squared and y equals x plus 2 around the x axis over the interval x from 0 to 2. So let's show on the paper.
So this is the example for the washer method. We have two curves, y equals x squared and y equals x plus 2, and it's on interval from x from 0 to 2. It's around the x axis as well. So I have to define the radii. So outer radius will be the x plus 2, and inner radius will be the x squared. So we can see we found the inner radius and outer radius. So we have the main formula, integral of 0 to 2 pi x plus r x square minus r x square dx, of course. So we find the rx and the little rx inner radius. So let's just put this to the main formula. So it will be the volume equals p 0 to 2 x plus 2 square minus x square dx. Let's open the something, I don't know. Okay, it will be the x squared plus 4x plus 4 minus x in the fourth dx. So let's reconstruct it into the usual integral. So it will be minus x4, right, minus x4 plus x squared plus 4x plus 4 dx. So this integral equals minus x5 plus x third divided by 3 plus 2x squared plus 4x. So let's put onto our formula already. So it will be the minus x fifth divided by 5 plus x third plus 2x squared plus 4x from 0 to 2. So if it will be 0, there is nothing. Here's the pi, so it equals pi minus 32 divided by 5. As I remember, plus 8 divided by 3 plus 8 and plus 8 as well, right? Yes. So what's equals? It equals 8b and a half, as I remember. Oh, that's half 8b divided by 3. So let me check the equation. So let's continue. Equals, this is equals 16 minus 32 divided by 5 plus 8/3 multiplied by p, and it will be the 884 divided by 15 multiplied by p. So that will be the revolution, or that will be the volume of our figure.
Why we should use the washer method? So there is a function and applications of washer method in the world. So for example, the first one is engineering and design. It used to calculate the volumes of components with complex shapes such as pipelines, wheels, and pistons. We also can use it in medicine, applied in determining the volumes of hollow organs, for example, vessels, blood vessels, and stomach, and etc. And we can also use it in science and research. It's used to analyze shapes and volumes of objects in physics, chemistry, and biology. And we also can use it in manufacturing. It helps us to calculate the material usage, for example, in producing vessels or flasks. So let's move to another one, the moments and the center of mass. So let's start with the moment. A moment of mass about a point or axis measure the tendency of the mass to cause rotation around that point or axis. So for example, we have a center of mass and it starts rotating. It can start rotating around the point, the center of mass. So let's start. Let me just explain you the center of mass. What is it? So the center of mass is the point where the entire mass of a body can be assumed to be concentrated for simplifying calculation. So the center of mass, it wouldn't be rotating around the axis or point. So it's just a point. It wouldn't be rotating around anything. So let's just watch for the example. Example number 1, the center of mass of a thin plate. So a uniform density plate, P equals 1, is bounded by the lines x equals 0 and x equals 2. So, and y equals x squared. So let's just make this question in a paper.
So let's move to the last question. We have a uniform density plate, so it's P equals 1. It's bounded by the lines x equals 0 and x equals 2, and the y equals x squared. So let's find the total mass at first. Total mass. Since P equals 1, that means the total mass is equal to the area of the region. So M equals integral from 0 to 2, because it's bounded by lines from 0 to 2, and bounded by the 0 to x squared, like the y equals x squared. So, and because of the area is 1, so we will be 1 dy dx. So it equals from integral from 0 to 2 x squared dx. So let's find the square of this integral. It equals from x squared divided by 3 from 2 to 0. So it's equals 8/3. So let's move to the moments. About the a-axis, so let's call it mx moment. So it's also the bound by the from 0 to 2 integral from also the from 0 to x squared. So that's what we're trying to do about the x-axis. So we should use the y. So there's a y dy and dx. So it equals the integral from 0 to 2. Y equals x squared, so it will be, let's put x squared. So x squared, so it's in the square. So let's put the x squared divided by 2. So dx. So the formula will be equals that everything will be equals to the x squared. That's the 0. That means 4 squared 16. That equals 4. So about the y-axis, so my. So from 0 to 2, from 0 to x squared by x dy dx equals from 0 to 2, that's x multiplied by the x squared dx. So it equals from I messed up with this. So I forgot to do the okay. So that will be the x fourth divided by 2. So integral from 0 to 2 dx. So it equals x5 divided by 5 multiplied by 2 from 0 to 2. So it will be the 32 divided by 10. So it will be the 16 divided by 5. So let's return to the y. So it's got a y x cube from 0 to 2 dx. So the integral equals the x4 divided by 4 from 0 to 2. So it's just equals the x3. So x4 divided by 4. Let me just recheck it. So I messed up with it. So this is just the x. So that x squared. So it equals integral from 0 to 2 x squared dx. So it equals the x3 divided by 3 from 2 to 0, from 0 to 2, and it equals 8/3. So we found the moments for the mx equals 16/5 and my equals 8/3. So we have the mass. So the coordinates that we should the coordinate of center of mass equals the my divided by m for the x, and for the y it's a mx divided by m. So my 8/3 divided by 8/3 equals 1, and 16/5 divided by 8/3 equals 1.2. So we're using the center of mass. Using the moments and total mass, we can find the center of mass of the object. In our place is a uniform density plate. So that's it.
So what's the application of mass and center of mass in life? So it can be used in the engineering and construction. For example, designing bridges, buildings, and other structures to ensure balance and stability. Medicine, it helps in understanding the human body center of mass, for improving the balance in physical therapy and sports medicine. It can be used in astronomy, determining the center of mass for systems like planet moon or star planet configurations. So there is a lot of application where can we use the moments and the center of masses. And thank you for your attention. That was me, Akhmetov Alim, CST2409079. Goodbye.